Hello everyone, welcome to He Classroom about Introduction of Physics. Today we are going to explore force and motion. In this chapter, we will work through several examples to see how Newton's second law can be applied to solve real problems. Now let's look at some examples of how to apply Newton's second law. We'll focus on two topics here. First, a puck moving on a frictionless ice, and second, how to solve for unknown force vector. Together, this example will help us understand both one-dimensional and two-dimensional forces. In this lecture, we will learn how to apply Newton's second law along a single axis. We'll use free body diagrams to identify the net force, break angled force into their x and y components, and ultimately determine an unknown force from a known acceleration vector. Let's see our first problem. In this example, we'll practice applying Newton's second law to a puck when one of two forces act on it. We'll consider three cases, part A, B, and C, where a puck moves along the x-axis on frictionless ice. In part A, a single horizontal force acts on the puck. In part B, two opposing forces act on it. And in part C, we introduce the angled force F3, where only its x component affects the puck's acceleration along the x-axis. The puck has a mass of 0.2 kg. The force F1 and F2 act along the x-axis with magnitudes of 4 newtons and 2 newtons. The force F3 has a magnitude of 1 newton and is applied at an angle of 30 degrees. In each case, our goal is to find the acceleration of the puck. To solve this problem, there are a few key ideas to keep in mind. First, we relate the acceleration of the puck to the net force using the Newton's second law, F equal to ma. Since the motion is only along the x-axis, we can simply think by writing the equations in terms of components. F net x equal to max and F net y equal to may. When motion is along just one axis, only that direction matters. But in two-dimensional problem, we need to treat the x and y directions separately. Finally, remember that the acceleration always points in the same direction as the net force. Okay, keep those key ideas in mind, then let's see case A. Here only one single horizontal force acts on the puck. The horizontal force causes a horizontal acceleration. The free body diagram for the situation is drawn here. Based on Newton's second law, then we will have F1 equal to ma1. Then ax should be equal to F1 over m. Put data into it, 4 Newton over 0.2 kilogram, then we will have the 20 meter per second square. The positive answer indicates that the acceleration is in the positive direction of the axis. Now let's look at case B. In this situation, two horizontal forces act on the puck. F1 in the positive x direction and F2 in the negative x direction. Its free body diagram is showing here. In Newton's second law along the x-axis, then we will have F1 minus F2 equal to max. Substituting the given values, then we will have ax equal to f1 minus f2 over m equal to 4n minus 2n over 0.2 kilogram equal to 10 meter per second square. So the net force accelerates the park in the positive x directions here. Now let's move on to case C, which is a bit more involved. Its free body diagram is shown here. In this case, the force F3 is applied at an angle, so it's not entirely in the direction of the park's motion. Even though the force is two-dimensional, the motion is still only along the x-axis. That means only the x component of F3 contributes to the acceleration. So along the x-axis, we can write F3x minus F2 equal to max. From the diagram, the x component of F3 is F3x equal to F3 cosine theta. Substituting this in, we will get ax equal to F3x minus F2 over m equal F3 cosine theta minus F2 over m. Now plug in the values. We will have 1n cosine 30 minus 2n over 0.2 kilogram, and it's equal to minus 5.7 meter per second square. The next sign tells that the net force and therefore the acceleration is in the negative x directions. Let's move on to the next problem. In this one, we use the acceleration to find a missing force. A 2 kilogram cookie tin is accelerating at 3 meters per second squared in the direction shown by the acceleration vectors here, over a frictionless horizontal surface. The motion is caused by 3 horizontal forces, but only 2 are shown here. F1 with a magnitude of 10 Newton and F2 with a magnitude of 20 Newton. Given the acceleration vector, where's the third force? In both unit vector notation and magnitude angle notation. The key ideas in this problem is that the net force on the object is the sum of all 3 forces, including the unknown one. And this net force is related to the acceleration through Newton's second law. So we can write F1 plus F2 plus F3 equal to ma. Rearranging to solve for the unknown forces, we will have F3 equal to ma minus F1 minus F2. This equation allows us to find the third force, use the noun forces and the acceleration. Since this is a two-dimensional problem, we cannot just work with magnitudes. We need to treat all quantities as vectors. So instead of simply putting values there, we have to add the vector ma minus f1 to as shown in the diagram. One way to do this is graphically. First, draw the vector ma. Then add the other vectors head to tails. The vector gives us the missing force F3. We can also solve this problem by applying Newton's second law in terms of component. First, we break all the forces and the accelerations into their x and y components. Then, we work one axis at a time. Let's start with the x-axis. Along the x-axis, we write f3x equal to max minus f1x minus f2x. Since the acceleration makes a 30-degree angle, so its x component is a cosine 50. Substitute this one, we will get f 3x equal to ma cosine 30 minus f1 cosine 1 minus 150 minus f2 cosine 90. Now put a value there. We will have 2 kilogram times 3 meter per second square cosine 50 minus 10 n cosine minus 150 minus 20 n cosine 90. Evaluating this, we will find f3x equal to 12.5 n. Now let's look at the y components. Use the same approaches along the y-axis. We can write f3y equal to may minus f1y minus f2y. The y component of the acceleration is a sine 50, so the substitute it in, then we will have ma sine 50 minus f1 sine minus 150 minus f2 sine 90. Put a value there, then we will have 2 kilogram times 3 meter per second square sine 50 minus 10 n sine negative 150 minus 20 n sine 90. And then we will have a value of 10 minus 10.4 n for the f3y. Now we can write the results in vector form. Using the components, we will find f3 equal to f3xi plus f3yg, and it's equal to 12.5i minus 10.4j. Now let's find the magnitude and direction of f3. The magnitude is f3 equal to square root of f3x squared plus f3y squared. It's approximately 16 Newton. And direction is given by theta equal to tan inverse f3y over f3x. It's approximately minus 40 degrees. So the third force has a magnitude of about 60 Newton and directed approximately 40 degrees below the x-axis. Okay, that's all for today. See you next class.